Okay, so in this lecture, we're going to be discussing the Yoneda lemma. And the Yoneda lemma is a kind of mind-bending but very useful result in category theory that involves functors from a locally small category to the category set of sets and functions between them. So in your homework, I gave you a sort of teaser problem for this that was supposed to sort of like warm up your brain for this lecture, and I'm just going to go over the solution to that problem now. So if you recall, the problem was to find or describe the set of all functions that have the signature bool to A. So take the function that takes booleans and returns some arbitrary type and returns a list of values of type A. So this is obviously a natural transformation. We have a reader functor here that takes a bool and returns the type that you're given, and we have a list functor here. So these are going to be essentially natural transformations from this functor, the reader functor, to the list functor. Now, so I'm going to sort of walk through the solution to this problem as if I don't really know any way of solving it. So let's think here. So the first thing I'm going to ask is there any way I can just return a constant? Just throw out the argument, the function argument, and just return a constant list of A. Well, there is one, but in general, we don't know anything about this type A, do we? So there's no way to provide a constant list of A without knowing about the type. Now, of course, you could, in theory, write a function for every single, in theory, you could write a function for every single type that returns a constant list of that. But the issue with that is that you no longer have, you break the naturality requirement, right, where if we were to lift a function from A to B to a function from list of A's to list of B's, that function would no longer commute with these natural transformations because the list of A's the list of these are constant. So we can't just return a constant list, except, of course, for the case where the list is empty. So if we just take, let's just call this first function foo1 of some function f, and it returns just an empty list. So that we got our function. We're going to just be looking through possible functions and see if we can find a pattern that would help us describe the set of all functions or the set of all natural transformations that have this signature. So that's our constant function. Now, if we want, I'm not satisfied with this. Obviously, there's more possible natural transformations. So let's try to make a function that returns an actual list of A's. Now, the only way to get a value of type A is to actually pass into a boolean to this function, right? So I'm just going to say, let's call this function foo_t, foot, and there's f, our function, and let's just return a list with one element, the result of taking f of true. Okay, that's good. That's another example of such a function. Now, of course, I could also return the result of taking the function on false. So let's call that foo_f. That's good. But looking at this, I maybe it'd be more useful to just have it return both. I mean, this is a list after all. It has more, you can have more than one element in there. So let's do foo b for Boolean, and we'll say it returns right. So that's almost like a perfect description of this function f. But the fact is, there's still more functions. In fact, there's infinitely many. Because when you think about it, each one of these results that I'm returning is simply the result of mapping over a list of Booleans, right? So any such function of this type signature is going to be the result of mapping over a list of Booleans, mapping the function that we're giving over a list of Booleans. So I'm just going to call it foo star f equal to L. And L is just some constant list, right? Let's say I just defined it somewhere else, right? So every single function of this signature corresponds to a list of Booleans, right? And the Yoneda lemma is going to show us that this fact is really just a special case of the Yoneda lemma. In fact, if you might notice that if you replace the Boolean type here with any other type, it would just those functions would just be described by a list of b. So so if we take b to a to list of a, I'm going to write an isomorphism sign. These are just the list of b, right? And in addition to that, you might notice, if you play around with this problem for a little bit more, that the functor here doesn't necessarily have to be a list functor. After all, this fmap works for any functor, not just lists. So if we have our b to a function and just some functor fa, it's isomorphic to fb's, the type fb. And if we just, an isomorphism is just a function, right? So you'll notice that we can just write something like this. And a little bit of rearranging. I mean, this is essentially you could think of it as a function that takes a type of f of b and returns one of our functions from a function to a fa. Or you could think of it as a function with two arguments, an fb and a function, and then returns a type of fa. And if we just switch the order of the arguments around, we get the fmap, the type signature of fmap. Right? So, there you go. That's almost like a Haskell proof of the Yoneda lemma. But we're gonna prove it for. I'm going to tell you what it is in a second here. I'm going to prove it from the categorical standpoint. So the Yoneda lemma, let's write it down. And in my opinion, it really should be called the Yoneda's theorem. Because it's such a significant result, and it's very useful in all kinds of fields that use category theory. Maybe not the higher category theory as much, but let's see. So the Yoneda lemma states that if you have a locally small category C, remember this means that for any two objects in C, the morphisms between those objects form a set. If you have any locally small category C and a functor, actually I'll write this notation down. I'm going to write H to the A. This is a functor from C to set. And we've already seen this functor. This is just a shorthand notation for the Hom functor, which is, if we fix the object A, we get a functor from C to set that maps some object to the set of morphisms from A to that object. Right? So this is a functor from C to set. And if we have some arbitrary functor, f from C to set, right? The Yoneda lemma states that the set of natural transformations, which I'm going to write nat, set of natural transformations from HA to F is isomorphic in the category of sets to the set FA, the result of applying this functor F to the object A. So just think about that for a second. It's a little bit mind-bending exactly what this is saying, but we sort of saw we already saw an example of this, and that's why I assigned this problem on your homework. You know, we have here a morphism from bool to A, and then we're looking at for the set. We're describing all of the natural transformations from this that takes, you know, it goes from the morphisms to the list of A, and those natural transformations are described by the list of A. So our F here in this example is the list functor, right? Now, seeing this statement initially is it's really kind of, you know, I said mind-bending a lot of times, but it really is. But let's get down to actually trying to prove it. So what we're going to do is we're just going to take our, so in C we have, in our category C we have some objects and morphisms, right? Got an object A, an object B, and some arbitrary morphism F going between them. And then over here in set, we've got the result of our two functors, our Hom functor. Here's our Hom functor. And I'm just picking A in this case. Let's just A to A, A, B, A, F, and down here we have our FA, FB, and our listed morphism FF. All right, good. So now, remember the requirement for natural transformations is that there has, for every object in C, there's a natural transformation in set. It's just a morphism in set that goes from Hom AA to F of A, and then there's a component for the natural transformation for B, which goes from Hom AB to F of B. I'm just going to draw these out. I'm going to name them phi. There's the component of phi for A, and the component of phi for B. All right. So far, so good. Now, but we haven't quite proven this lemma yet. We just drawn a diagram. But so what's really kind of cool about the Yoneda lemma is that it takes an arbitrary category and an arbitrary functor, right, and it brings it down into this, which are, categories and functors are very abstract, high-level things, but it brings it down into this category of sets. And in set, we know that sets are just bags of objects, and the functions between them are just mappings between those objects. You put an element in your bag into the function, and you get another element out. So we can sort of we can just do set theory to prove the Yoneda lemma from here. So what do we know about this Hom set here, Hom A to A? That's a set of all morphisms from A to A. Well, we don't really know much. A is just an arbitrary object in our category C, but we do know one thing. From the definition of a category, there has to be one morphism in there, at least one, and that's the identity on A. So I'm going to draw sort of another commutative diagram over here, except this is going to be the actual element. These are going to be showing how these morphisms, which are functions in set, are mapping the elements in these sets to each other. So we have our ID A. Now this morphism is essentially composing the morphism F with the morphism given in here. So this is going to map to just F. I mean, if you map the identity with anything, you get, with any morphism, you just get that morphism, right? Now the question is, what do our natural transformations do? Well, we don't really know much about this natural transformation, or even this set FA, right? So I'm just going to say I'm just going to give a name to what the identity maps to. I'm going to call it U, right? That's just some arbitrary element in the set FA, and with the necessary requirement that U is equal to phi sub A of the identity of A. Okay. And so U, this lifted F function here, we don't really know anything about it. Right, but we could just say, all right, it maps U to FF of U. All right, and since this is a natural transformation, we have the additional requirement that our B component has to map this F to the same element. So I'm going to go back and erase this part here, just to really emphasize this. We've essentially defined how this phi B function acts on the Hom set Hom AB. I'm going to write it out. Phi B of F is equal to the result of applying the lifted F to U. So essentially, this natural transformation phi is completely determined by which element in FA the identity is mapped to, right? And if you still don't believe me, let's try doing it with a not a homomorphism, an automorphism on A. So if we take the, let's move down a little bit further. We take A. You might be wondering, how can it be completely determined by just what it maps the identity to? Well, it comes from the requirements of what a natural transformation is. Remember that a natural transformation has one component for each object in A. So these two are the same function. Phi A here is the same as phi A here. We take our ID A, maps to U, maps to F, the same. It works exactly the same for even for automorphisms, right? This natural transformation, even the one from HOM AA to FA, is still determined entirely by what it maps the identity to. There's only one possible natural transformation that maps the identity to U. And now, of course, there's other elements in FA, aren't there? Which means that for every element in FA, you have a natural transformation from HOM AA to FA. And that's the Yoneda lemma. Now, let me look at my notes for a second here. All right. So, what this gives us as category theorists, how are we going to use this? Well, I'm going to give you the definition of a representable functor. Now, a representable functor are it's messy, I know. But a representable functor is a functor from C to set, F, such that there's some object A. I'm just going to do the shorthand. There exists an A in the collection of objects of C. Some object A in the category C, such that the functor F is naturally isomorphic to the HOM functor given by A. Right? And essentially what a representable functor is it's a way of representing our category as a more concrete thing. Sets are actually sets of values, right? Instead of just an arbitrary objects and morphisms. It's a set of values and a way of mapping between those values. So you can sort of think of our category here, C, as like a high-level language. At least in terms of mathematics, the category is it's like a declarative language, right? Where we're just describing the behavior of the function. You're not describing how the function actually implements that behavior. And then in set, we are describing how the function implements that behavior. So these representable functors are like compilers for our category. Now, there's a few things about representable functors. So we have this functor F is there for this representable functor. There exists an A in C, and that A is an object which has a universal property. So rule, I'll type it out so it's easier to read. So essentially we're looking for an isomorphism between f and this Hom functor. Now, in order to find it, we're going to use this universal property, which I'm going to describe here. So, a natural transformation from given by an element u in FA is iso if and only if and only if for any x in C for any object x in C and element b in Fx, we have the following requirement. There exists a unique morphism. All right, for also a unique morphism F from A to X, such that the lifted F applied to U equals D. I'll draw the diagram so it's a bit easier to understand. We have our A, we have F of A, we have our, I'll just call it U of A. I know it's not a Greek letter, but this is the natural transformation given from mapping the identity of A to the element U in F of A. Okay, that's what that means. And we have Hom sets. Let me go over a little bit. See, and Fx, and of course the components of our natural transformation. Dx. And in our category, well, we have there exists a morphism from A to X, so if we lift it, we get a morphism going like that, and this commutes, which is the requirement for naturality. Ugly V. Okay. This is still a little bit abstract, I think. I'm going to give an example here. But before I do that, I need to define a few terms that describe functors. So, we call a functor full if it is surjective on Hom sets. This essentially means that the Hom sets in the domain category, every morphism is, it's mapped to some morphism in the codomain category, but every single morphism in the codomain category has some morphism that maps to it in the domain category. And a functor, call a functor faithful if is injective on Hom sets. You can think of this as almost being like every single morphism is faithfully represented in the codomain category. It maps each morphism to a unique one in the codomain category. So a full functor sort of covers the entire set of morphisms in the codomain. It fully describes all of the morphisms in the codomain. A faithful functor is faithful to every single morphism. It doesn't ever map two morphisms to the same one in the codomain category. So with these, I'm going to be reusing these later on in the lecture too, but I'll give you a definition right now. I'd mentioned concrete categories in the first lecture, I believe. And I'm going to give you the actual definition now. Category is a category C, a has a faithful functor U from C to set. And we call this faithful functor from C to set the forgetful functor. Now, remember that when I described concrete categories in the first lecture, I mentioned that they're sort of categories that where the objects in a certain sense are sets. Remember, we described a monoid in that first lecture, and that is a kind of algebraic structure that has, I'm just going to rewrite these. It's a set X and a operation, I'll just write dot, right, such that for all A, B, and X, A dot B is also an X, and the operation is associative, right? I'm not going to write that one out. But there also exists an identity E in X, such that for all A, B, and X, E dot, for all A and X, E dot A equals A dot E equals A. E is the identity element of this monoid. Need a bigger tablet. So that's our definition of a monoid, right? So you could think of monoids as like a set, but with additional structure added, right? And then the monoid homomorphisms in the category of monoids are functions between sets that preserve that structure. So the forgetful functor then is essentially a functor that maps the monoids in our category of monoids to the underlying set. We are essentially forgetting that structure. And it maps the functions, the monoid homomorphisms, to just the underlying function in set, which is still the same function, and the underlying set is still the same set, but we've forgotten, essentially, what it means that they're monoids. We've forgotten that there's this added structure to it. So that's a forgetful functor, and a forgetful functor is a representable functor. um, I'll give you the actual object in the category of monoids that gives us our Hom functor that's isomorphic to the forgetful functor. It is, drum roll, set of natural numbers under addition. That's a monoid. You can check. It's not too difficult. This has identity 0, right? So it is identity, right? And this is, the rest are just positive numbers. And I'll prove it. Well, I'll just sort of draw out a diagram. I'm not going to really prove it. Maybe not, enough to satisfy you. But so the set of monoid homomorphisms from the set of natural numbers under addition to itself. And we have the underlying set. This would just be the natural numbers, right? It's just 0 and all positive integers. And if we have some arbitrary monoid, x, now, the element of the natural numbers that gives us our natural isomorphism between the Hom functor and our forgetful functor is 1, the integer 1. So if we have some monoid homomorphism F, that's actually so this would actually be an element of this set, right? And maybe drew this too big. Oh well. I'll draw our other diagram over here. And that's the identity to 1. Now why is that? This functions is going to map to F. And this is just going to map to, F of 1. Some element in our monoid X. But essentially what this means is, we couldn't have it be, we couldn't have mapped to 0, right? Because that is actually the identity for this monoid, natural numbers. And a requirement of monoid homomorphisms is that they have to map the identity to the identity. So that won't work for any arbitrary monoid homomorphism. You can't describe them that way. But if we take 1, we could just map that to an arbitrary element in our arbitrary monoid. And then we take, I'll just call, you know what? I'll say that it maps it to V, all right? And then, the thing about the natural numbers, we call this element 1 the generator, because every single natural number can be represented as essentially just adding 1 to itself a certain number of times. So this natural transformation it would map, or this, it maps 1 plus 1 to v plus v. Oops. And 1 plus 1 plus 1 to v plus v plus v, and so on. Right? So what we've done here is we've essentially given a way to implement our monoid category in the category of sets using this forgetful function. All right. There's one more thing I want to talk about, and that is the Yoneda embedding. All right. So we have our well, okay, I'll talk about the forgetful functor a little bit more. We've sort of been describing our category as our category of types, right? I probably should add, I haven't added this already, but Haskell, the types in Haskell are not necessarily a category, right? But we can use category theory to inform our engineering in Haskell or any other functional programming language, or any programming language really. Even if the types of that language don't necessarily form a category, we can still use the lessons from it to make good choices in our engineering. But we have our category of types, so to speak. We'll call this one an actual category, right? And we can sort of say, okay, our representable let's just say there's a forgetful functor for this category. Now we can actually talk about how functions actually map specific elements of our types to other elements, right? It's almost like our compiler, right? I mentioned that already. So our representable functor, our forgetful functor, is our compiler for our high-level language down to a low-level language. So our one more thing, our Yoneda embedding. Let's look at our Ham functor again, except we'll expand it out. All right, our C. This takes 2 arguments this time, and if you remember, the first argument is contravariant, which means it reverses the arrows in our category. All right. Now, of course, the category of categories is Cartesian closed, so we can curry this and get a contravariant functor from C to the functor category of functors from C to set. And what this is doing, this is our Yoneda embedding. It lets us embed a given category into this functor category, and instead of studying the category itself, we study the category of functors from C to set. And this can be pretty useful to us, and I'll explain why. The reason it's useful is that this mapping, this functor, I'll just call this E. E is both full and faithful, which means it's bijective on the Ham sets of C. And what this means is that if we have E of X isomorphic to E of Y, all right, so these are, E of X is a functor from C to set, and E of Y is another functor from C to set, represented by 2 objects in C. And in fact, they're Ham functors. I'm just going to, you know what? I'll write it like this, because it is a Hom functor. Use our shorthand notation. Right? H x, if that's isomorphic to H y, this implies that x is actually isomorphic to y in C. And this is a natural isomorphism, obviously, because these are functors. Now, this is pretty useful because I've been having you proving that objects are isomorphic for, you know, the past few assignments, right? And this is the first one where we don't have to remember that we have our we have this way of describing isomorphic, you know, we have this way of finding natural isomorphisms in our functor category by, you know, finding this element in our. So I'll give one example, and this is, you know, the Yoneda embedding and the Yoneda lemma are very useful for proving a lot of things. Unfortunately, we're not quite at the point yet in this course where I can explain the useful stuff that it's proving. And in a couple lectures, I will be there. But so this example is a little bit contrived, but it'll still show you how we can use the Yoneda embedding to prove isomorphisms. So I want to prove the following isomorphism in our Cartesian closed category. Essentially means that the terminal object is isomorphic to the exponential. Terminal object 1 is isomorphic to 1 to the a. When you think about it, this is the set of homomorphisms from a to 1. The definition of the terminal object requires that there be exactly one morphism from any object to the terminal object. So if we consider the terminal object to be a set with a single element, this is kind of apparent. But remember, we're doing this in category theory. We don't know what exactly this terminal object is, and we don't really, you know, the way you could interpret the exponential is the morphisms, right? The set of morphisms from a to 1, but we're not interpreting that way. We're describing it in terms of these universal properties that are in their definition. So we, you know, this seems like it would be right, but we got to prove it using category theory, not just set theory. But as it happens, we are going to prove this using set theory, using the Yoneda embedding. Or are we? It might not actually be sets that we're talking about here. We're actually talking about functors. Okay, so let's just draw some diagrams. We've got the 1, the A, 1, there's a terminal morphism, I'll call this TE, and our definition of the universal property of the exponential states that we have this evaluation function, which is also a terminal morphism. I'm not going to call it that just to avoid confusion and clutter. And we're looking for a morphism from 1 to A. So let's try, and of course there's a terminal morphism right there. I'll call this TP, P for product, E for exponential, right? And the universal property of the exponential means that we have a morphism going from 1 to 1A. I'll call this lambda TP. And of course we take the product of that with the identity of A, and those commute, and that's all good. Now, we know that TE after lambda TP is the identity of 1. That's just from the definition of the terminal object. We don't really know. We want to prove that lambda TP after TE is the identity of 1 to the A, but it's not apparent. It's not really clear how we're going to do that yet. Well, let's embed these objects in our functor category, right, using the Yoneda embedding. So, let's still plenty of room. Got hom1a I'm actually these are actually sets that I'm writing out here, but I'm just doing that so that it becomes apparent when I write out the the components of the natural transformations, what's going on. And we have for some arbitrary object in our category X, all right. Now, our definition of a representable functor is one that's isomorphic to a Hom functor. Now, these are both Hom functors, but let's say that this is we want to prove that h to the 1 is naturally isomorphic to h to the 1 to the a. And if we prove this, then from the fact that the Yoneda embedding is both full and faithful, we know that these, well, our Yoneda embedding is going to take, so it's contravariant, remember? So to get a natural transformation from Hom1a to Hom1, we need a morphism from Hom1 to 1a. That's this one, lambda TP. I'll write it out like this. Component of this is that's the component of this natural transformation for the object 1a. And the component for 1. Looks good so far. Now, we have our arbitrary object x here, and let's say we have a morphism, an arbitrary morphism z. In order for this natural transformation to be a natural isomorphism, remember, where is that definition? There needs to be a unique morphism from, oh dear, I've lost it. Oh, there it is. Okay. There needs to be a unique morphism from 1a to x that such that that morphism, I'll write what it is in a second, but that morphism after lambda TP is equal to v. Now, if we compose v with TE, we get a morphism that at least has the right domain and codomain. So this is, oops, that's not right. It is v after TE. Right? Okay, great. So let's lift that into our category of sets. Okay. All we have left to prove is that this diagram commutes. So how are we going to do that? Well, you know what to do. We draw our little identity of 1A. This maps to, so this is this natural transformation just precomposes lambda TP with the identity on 1A, and we get a morphism from 1 to 1A, which is lambda TP. So the identity maps to lambda TP, and that's the Yoneda lemma, right? So this natural transformation is defined by this specific morphism, an element in this Hom set, which is a morphism from 1 to 1A. Right, so it maps that identity to that morphism. And we know that if we compose V after TE with ID, the identity, we're just going to get V after TE. And then, so this lifted morphism, the function between these Hom sets, and it also just composes V after TE with lambda TP. So this is going to map to V after TE after lambda TP. And in Yoneda lemma, we know that this commutes, but we don't necessarily know that this is equal to V yet, or do we? We saw before, using the definition of the terminal object, that TE after lambda TP is the identity on 1. So this is equal to V after the identity on 1, which is equal to V. And we've just proven that lambda TP is an isomorphism using only the fact that when we compose it with the terminal object, the terminal morphism TE, we get the identity on 1. We didn't have to prove it for this one. Now, this is kind of a contrived example, but it shows you a way of how embedding your category into this category of functors and then using the properties of representable functors, you can prove things. I don't know if this is really easier than the alternative way. I haven't actually tried to prove it the alternative way, but it is a way to prove it. So that's it for today. Homework solutions will be up tomorrow. The homework for this week, I'm not sure if there's going to be any. Like I said, the really useful aspects of the Yoneda lemma are not going to really come around until a couple lectures later. So there might just, if there's no homework uploaded before Friday or by Friday, you can just assume that there's not one. So you'll have another week off on the homework end. So that's it. Bye, everyone.